Okay, so we were in the middle of this design problem where we started with the state diagram and completed the PSNS table. But now we need to provide excitation equations and output equations in reduced form from this table so we could go ahead and draw our FSM circuit. Okay, so we have 4 excitation variables, which provides our next state decoder logic, and our output, which provides our output decoder logic. Okay, so I went ahead and made a nice table in Excel instead of writing it by hand. How nice. And I'm going to now refer to this table to create my equations. So let's start with D. I'm going to put D here in a circle. So guess what? Since we want a reduced form for D, we're going to use a wonderful K-map. Here comes our K-map for D. For D. And I'm going to go ahead and label it A naught, B naught, and C naught. Oh, that's C, sorry, not C naught. Okay, and I'll go ahead and fill it in. 0, 1, 2, 3. Row 4, 4, 5, 6, and 7. Okay, so we'll go ahead and circle our ones. We can circle these ones together. Sorry, I guess I'll go ahead and circle it in a different color. We can circle these. We can circle these. The don't care doesn't help us in this case, so we don't need to use it. And this one is all by itself. So we're going to get D is equal to, this one by itself is going to be A, B naught, C naught. A, B naught, C naught. Or this middle circle here is going to be A naught. Sorry about that. It's going to be A naught C. And then we have this last circle, which is A naught B. Now, because we used A, B's, and C's, we want to rewrite this in terms of Y1, Y2, and Y3, where Y1 is A, Y2 is B, and Y3 is C. So this is actually going to be D is equal to Y1, Y2 naught, Y3 naught, or Y1 naught, Y3, or Y1 naught, Y2. So this is our reduced form for D. And guess what? We get to do this for every one of these columns. So let's go for the T flip-flop now. T I'm going to do here in orange. So T flip-flop. We're going to have 0, 1, 2, 3, 4, 5, 6, 7. Alright, so let's go ahead and circle for the T flip-flop. We're going to have these ones circled. And now you have a choice. You could have this one circled with the don't care or circled with this one. I'm going to go ahead and circle it with this one. So we're going to have D. Sorry, this is now T. T is equal to, this is going to be B naught, C naught. Or this bottom circle is going to be A, C naught. And again, let's convert that to our Y's. So it's Y2 naught, Y3 naught, or Y1, Y3 naught. Okay, so instead of me doing the K-maps for everything else, I'm just going to go ahead and write it down and you can check it for yourself. So I'm going to put the J. J is going to be equal to Y1, Y2. And K is going to be equal to Y1 or Y2. And Z is going to be equal to Y1 naught, Y3 not, or Y1 not, Y2 not. Okay, so in order to get all these that I just wrote, you would have to put each of these columns into a separate K-map per each one and circle your bubbles and get your result. Okay, so we have now provided the next state decoder logic, which is all the flip-flops, the D, the T, and the JK, and our output decoder logic, which is Z. So now we can use that to go ahead and draw our circuit diagram. And I'm going to do that on the next page. So in our circuit we have 3 flip-flops, a D flip-flop, we have the input D and the clock, output is going to be Y1, we're calling this Y1 and Y1 not, instead of calling it Q so we can distinguish it from the other flip-flops. We're going to have a T flip-flop where we have a T and a clock, and this is our Y2, Y2 not. And we have our JK flip-flop. JK and the clock, and Y3, Y3 not. Okay, so our excitation equations I had on the other page, but I'll go ahead and just write them down here. We had D. D was Y1, Y2 not, Y3 not, or Y1 not, Y3, or Y1 not, Y2. So in order to make this neater, I'm just going to go ahead and write that like so. We're going to have the AND gate here for the Y1, Y2 not, and Y3 not. Another AND gate for the Y1 not and the Y3, and another AND gate for the Y1 not, Y2. And we're going to put these all together into an OR gate, and that's going to be our D signal. So these, again, you could actually draw a wire coming from this feeding back around. So wherever you see Y1, it would be coming from this Y1. If you see Y2 not, you could grab it from the Y2 not and draw it back around. But as you can tell, it's going to get very messy, so I'm not going to draw it like that. So then we'll do the T. The T, we had 2 AND gates. The first one was Y2 not, Y3 not, and then the Y1, Y2 going into an OR gate. The output of that was for our T. And then we had the JK. The J was an AND gate between Y1 and Y2. And the K was an OR gate between Y1 and Y2. Okay, and then we have our output Z, and remember that Z, again, I'm just going to draw it off to the side. Z was Y1 not, Y3 not, or Y1 not, Y2 not. That goes into an OR gate. And there's Z. So here again we have our finite state machines with the state variables or the state registers. We have the next state decoder logic, which is all combinatorial, and the registers are our flip-flops, which are sequential, and then we have the output decoder logic, which is also combinatorial. So there you have it. We now went from a state diagram back to a circuit diagram, and so now if you were given this to begin with, you would also be able to go from this back to the state diagram. All right, great.